All right, hi everybody. Welcome to Tuesday. Last little bit, we're in the final little stretch before the AP test. So kind of what we're looking at today is just going to be a review of electric charge and force, kind of the ideas around charge, where it comes from, how it happens, and then this force that comes out of this idea of charge. So what we're going to do today is a quick little review lecture. Hopefully it's quick. I'm going to try to make it real fast. And then some more multiple choice style questions. I know we don't have multiple choice questions on the actual AP test, but it still helps us get down concepts and helps us kind of work through some of these ideas that are tricky. I think that electric charge and force are pretty tricky topics, so it helps us to kind of get some conceptual understandings. I feel like looking at your guys' work, we're doing a good job kind of with the format and structure of the AP style test, and we're in the home stretch and we kind of have to be in crunch time. So I'm just going to make these a little bit shorter. And then upcoming, so a quick look at what we're doing to finish up the content in the year is we're doing some field and potential stuff tomorrow, so kind of the harder part of electricity. And then on the 7th, we'll kind of practice that. On the 8th, we'll do a comprehensive circuits review. And then the 12th is the Tuesday before the AP test. That is when we'll have a little bit of last little tips and stuff about the AP test. So I'll kind of make a video being like, here's what we have to do. Or I may do that a little bit earlier too, just so we can get all the problems worked out beforehand. But sometimes there will be, hey, this is what we have for the AP test, this is what you're allowed, this is what you can do. It's kind of interesting. We get an equation sheet along with just open notes. You can use whatever you want. So hopefully I'll go in here, I'm going to try to make like a big note sheet, but I'll figure that out. But there will be a day where we kind of talk about what does the format look like, how are you going to do it, and how's this going to work. And then the 14th is last day for seniors, which is crazy. And then, yeah, so what's going to be do is just practice. So to start off thinking about charge, we have to think about what's actually causing this charge. So we've learned in chemistry that the universe, all matter, everything, well, not the universe, every piece of matter in the universe is made up of atoms. And we know that these atoms, in the middle, we have the small and dense nucleus that's made up of protons and neutrons. And throughout chemistry, we saw a lot of different models for electrons and the atom in general. But it doesn't really matter as long as we have this idea that we have protons in the middle and the electrons are outside of it. So what we're using is this kind of cloud model where we're saying, oh yeah, this cloud represents a probability of where these electrons could be. But as long as we know the electrons are on the outside, they're not bounded, that's really all that we need. So we have electrons on the outside. And this charge is an inherent property of electrons and protons. So that's kind of a weird thing. It's kind of an interesting thing. We're used to like all matter having mass, and we say that this mass is an inherent property of our object. Like if I have this pen, I say, okay, the amount of mass in this pen is inherent to this pen. If I go to the moon, it'll have a certain amount of kilograms. If I stay here, it'll have a certain amount of kilograms. That's inherent to this matter. Electrons and protons, same exact thing. This charge is an inherent property of them. They just have it. So electrons and protons are really the basic charges in matter. If anything is charged, it's because of these electrons and protons. There's no other sources of charge. The charge has to come from electrons and protons. And if we're thinking about how can objects become charged, it's really because of this balance of electrons and protons. So electrons and protons are going to have an equal magnitude of charge, but they have opposite signs. We know from everything we've done before that protons have positive charge and electrons have a negative charge. And if they have an equal amount of charge, if we come across some sort of macroscopic scale object and we say, okay, it has an equal amount of protons and electrons, then we say there's no net charge and this object is electrically neutral. The amount of positive charge is going to be canceled out by the amount of negative charge, and overall we have no net charge. This is going to be an electrically neutral object. Then what we can say is if an object has more electrons than protons, it has a negative charge. Overall, if we counted out all of these charges, we'd have more negative than positive. The positives, the protons, would cancel out the electrons, and we'd be left with an overflow of electrons. So we'd have a net negatively charged object. And then for a positive object, we'd say, okay, it has less electrons than protons, so we have more protons, and we're left with a net positive charge. And objects are going to become charged if they either gain or lose electrons. So we want to think about charging objects. If we want to say, oh, the protons are moving, the electrons are moving, but we said these protons, these are in the nucleus. These are tightly bound. These don't really move, but the electrons, those are freely flowing. If we look back to this picture of the atom, the electrons are freely flowing. They can go wherever they want, kind of. But the protons, they're stuck. They're bound to the nucleus. So objects are going to be charged by either gaining or losing electrons, not protons, electrons, because the protons are tightly bound The electrons are loosely bound. They can be removed or added with little effort. And the consequence to gaining or losing electrons is pretty huge. We have a few ideas, two ideas kind of here. We have this main idea that objects can be charged by either gaining or losing electrons, which means that the only way that something can become charged is if it gains or loses electrons, and those electrons have to come from somewhere. So we have this main idea that charge is going to be conserved. The amount of charge in the universe or throughout any charging process is always going to stay the same because those charges have to come from somewhere. If something's going to gain electrons, those electrons had to come from another object. We can't just create charge out of nowhere. It has to come from something else. So the electrons have to come from somewhere or go somewhere. We can't just create charge. It has to come from these electrons. So charge is conserved. In a system, charge is going to come from one thing and go to another thing, or leave one object and go to another object. And then another kind of main idea that plays along with the conservation of charge is that charge kind of comes in these discrete packages, this defined number of charge. So what we say is protons and electrons have a charge that we label E, which is the fundamental charge. And this E has a value of 1.6 times 10 to the negative 19th coulombs. And it's kind of like, I like to think about it as like a penny of charge. It's the smallest amount of charge that we can move around. So every object that's charged is going to be some multiple of 1.6 times 10 to the negative 19th. If we have an amount of charge that's like less than 1.6 times 10 to the negative 19th coulombs, that doesn't make any sense because that couldn't have come from somewhere. We have to get this charge by moving electrons. So we can really have any multiple of 1.6 times 10 to the negative 19th coulombs as our charge, but nothing less than that. We can't have anything that's not a multiple because we have to create charge by actually moving these electrons. So it all has to be discrete pieces of that. Just like when we think about money. Like we could have, it doesn't make sense if you're saying, oh, in my bank account I have 0.025 cents. Like that doesn't make sense. Our money doesn't come in that small of units. So it has to be made up of pennies. We can't go smaller than a penny, but we can create a net charge by having a lot of pennies. And then when we're thinking about this, we're saying, okay, well, things become charged if electrons move. So what determines how easily electrons can move? And this is something that we know very well. It's going to be based on the material. And we really have two types of material that we're going to worry about in this class. We're either going to have conductors or insulators. When we think about conductors, the main material that we think about with a conductor is going to be metals. So anything that's metallic is going to be a conductor. And metals are going to be conductors because the valence electrons are weakly bound to the nucleus. So we've learned about valence electrons in chemistry. We have kind of different levels of electrons, and the outer level is going to be our valence electrons, the one that we either share or lose when we're bonding. So when we have metals, we have these valence electrons, and they're weakly bound to the nuclei. We just have a few, they're weakly bound, and because they're weakly bound, they can kind of like wander through our material freely. They're just like, I'm not super bound, I can just kind of go wherever I want. So this creates what we have more often than we maybe should have, I don't know, what we've called the electron sea. This idea that we just have this freely flowing sea of electrons, and they're just kind of in this material. They can move wherever they want to. They're not bound to this protons, just like a sea. If you look at the sea, the water can just go wherever it wants. It's not bound to any one location. So we have the positive nucleuses over here, and the electrons, they don't belong to any one metal ion. They just kind of go all over the place, just like one little bit of water doesn't belong to anything in the sea. Just makes up the whole sea. So we have the electron sea. And then the other type of material is going to be an insulator, and that's going to be kind of the opposite. That's going to be a material where the electrons are pretty much bound to the nucleus, and they don't really move that much. They can locally move, they can kind of shift around the nucleus, but they're not going to come unattached. They're not going to leave the nucleus. They can kind of shift, but overall they're not going to be freely flowing. They can move around, but they can't move away. So here we have kind of an example of an insulator, and we see, okay, these little shells right here are kind of like our inner, the nucleus, the inner everything. We have the nucleus, and we kind of have some other electrons maybe, but these other ones, the electrons on the outer shell, tightly bound, can't really move. But when we see over here, when we look at a conductor, these electrons, they can just move wherever the heck they want. So we have different methods of charging. So we've talked about, okay, we have insulators, we have conductors, objects can get charged by gaining electrons, but how does this happen? What are the methods that we can do this? So the first method, the one that we did the most when we were doing charging in class, is charging by friction. And charging by friction is just a method of delivering charge by rubbing two objects together. It's like when we charged stuff in class, we took that rabbit fur and we rubbed it on either the PVC or one of those glass rods, and we were able to charge the PVC or those glass rods. And what you're doing here, it's not too bad. It's what you think it would be. You're literally rubbing the electrons off one object and onto the other object. So if you have the rabbit fur, it's got the electrons. You are literally scraping off those electrons. And the reason this happens, you don't have to know it, is but one object wants the electrons more than the other one. So we call that electron affinity. One wants to give them away, and one is more wanting of gaining them. So if we kind of have this example here, we have John Travoltage, which is a classic, but he's not going. There we go. You can physically scrape the electrons off the carpet, and they go into the little John Travoltage. You're physically scraping them up. You're taking them from the more gaining of the electrons. So it gains them because we're physically scraping them off the carpet. Here's just a little diagram in a textbook that I have that I thought was kind of helpful. But it's what we see. So we say, okay, they start off neutral, they're not charged, we don't have any net electrons in any of the other one, or any like net protons. So these neutral objects, we're kind of going to represent them, we can rub them on there. And this one, it gained the electrons from the rag, or from the rabbit fur. It had to come from somewhere. We have this idea that electrons, or charge, is going to be conserved. So the electrons came from the rag and onto the rod. And then we're left with a net negative and a net positive, respectively. Another way of charging. This one's a little bit more confusing, but it's kind of cool. So we have this charging by induction. So this is going to be a method of charging where you don't actually have to touch the objects to each other. So it makes use of this ability of a conductor to have this electron C. It has this, hey, we can move these electrons wherever they want. And charging by induction really makes use of that. So it's a way of separating charge to create electrically polarized objects. So let's look at a little simulation for this. Come on. So this one, we don't end up with a net charge, but it kind of shows us the process. If we took this final step and we kind of separated them, then we'd be good to go. But what we see here is we have this neutral rod, and this has an even amount of electrons and protons. So it's neutral, and it's going to be a conductor. So we can move these electrons wherever we want within the rod. We just need something to do that. So what we're going to do is bring a negatively charged rod closer to our conductor. And what we see is, well, this negatively charged rod is scaring away, or repelling, I guess is a better way. It's not physically scared of it, but it's moving the electrons from the conductor away. And we said, hey, it's a conductor. These electrons can move wherever they want. So they move away from the negatively charged rod. So we see, hey, they're moving away. Now we have this charged object. Over here, this side has a net positive charge. The charge over here, this side has a net negative charge. So we have two charged sides. We've used this polarization. We have a positive side and we have a negative side. If we came in here and grabbed those glass beakers and separated them, we kind of have a split down the middle of this rod, we'd have a rod that is positive and a rod that is negatively charged. And we can do the same thing with the positive one, except for this time the electrons are attracted and we can pull them apart. That's charging by induction, and here's just kind of an example of it. Same kind of thing, we have the two metal spheres, they can conduct. We bring a negative charge over here, it repels the electrons away from A to B, so we're left with a net negative on B, a net positive on A. When we separate them away from each other, we're left with net A as positive and B as net negative. And then another way that we can do this is we can make use of grounding. So grounding is a process that we did when we were playing with electricity because we didn't want to keep it on us. We said, hey, we want to get rid of this electric charge. And that's really all that grounding is. Like when you touch the Van de Graaff or something and you had this electric charge on you and you didn't want it anymore, you would just touch something and those electrons would go away. They would flow through that object to the ground. So the ground is kind of like this giant well of electrons. It'll either take excess electrons or it'll give electrons to objects that are low on electrons. So it's kind of like this giant bank that we can either take from or give electrons away to. But if we kind of see this example, if we just have one object, we do the same thing where we have, okay, let's bring a negative charge next to our neutral metal sphere. The electrons are going to be moved from where they were before to the other side, and then we're left with a positive side and a negative side. In this case, you just kind of come in, you bring your finger, and you are touching the ground, hopefully, and the electrons will flow through you to this ground because the ground is ready to accept electrons. So then we took the electrons away, we're left with positive charge, and then when we move our balloon away, we have this positive charge throughout the sphere. All right, the final method that we're going to talk about is charging by conduction. So this one's kind of the most simple one, the one we probably think of the most when we think about charging. And this is a method of just kind of touching two objects together. So you're just going to say, hey, I have a conductor, I have another conductor, I am going to physically bring, or you don't even need a conductor and conductor, but you're just going to say I'm going to physically bring the objects next to each other, and these electrons will jump from one to the other. So instead of like brushing them off with friction, they're just literally jumping from one to the other. So excess electrons will jump to the neutral object, giving it a negative charge, or they'll jump from the negative charge, or the neutral to the electron deficient one, making it positively charged. But we kind of have a example of this. This is something we're used to, and this is actually not charging by conduction. I don't know why I have this one in here. Let me pause this.